Hey guys, welcome back to Bottom Up Chem. In this video, we're going to be looking at condensation reactions, the basic reactions, and then we're going to look at also condensation polymerization later in the video. You'll be pleased to know no mechanisms required here. So, little thing to get started with, draw the mechanism for the nitration of benzene and state how the electrophile is formulated. Pause the video, give yourself a moment for that. Okay, for our mechanism, remember we're going to have the NO2 plus ion is attacked by the double bond, giving our intermediate with the NO2 and hydrogen with the positive charge. The electrons from the bond with the hydrogen come down, reform the delocalized system, and the HSO4 ion picks up our hydrogen. That HSO4 was created in the reaction that produces our electrophile, the reaction of sulfuric acid with nitric acid. So let's turn our attention to condensation reactions. Basically, a condensation reaction is a reaction where two molecules join together and they form water as a byproduct. They can also form other molecules as byproducts, but we're only going to look at water as a byproduct. We're going to focus on two. The first being the production of esters by reacting carboxylic acids and alcohols, called esterification, and the second being the reaction of carboxylic acids and amines, which form amides. Now, you don't need to know the mechanisms for these reactions, but you may need to be able to draw the products of a given reaction. So, looking more closely at making esters, as we said, we need a carboxylic acid and we need an alcohol. This is going to form an equilibrium to form our ester and water, and we're going to use a catalyst of concentrated sulfuric acid. This works in two ways. First is an acid catalyst that increases the rate of reaction, but also it works as a dehydrating agent, which allows the water to be removed from the products. And if we think back to our equilibrium, that's going to shift the equilibrium to the right hand side and allow us to produce more of our ester. If we're drawing these reactions, what I tend to do is try and face the OH groups of both the alcohol and the carboxylic acid. So here I've got methanoic acid and ethanol. Face the two alcohol groups to each other, and then I can see quite clearly where the water is going to be removed from. So when I draw my product, I'm less likely to make a mistake, and you'll see here that I draw my product, which in this case is ethyl methanoate. We'll go through the naming of these in a few moments. And if we look at the production of amides, we're going to see a lot of similarities. We've got carboxylic acids, except in this case, we're going to be adding amines to that, forms an equilibrium to form our amide plus water. Now, you don't need to remember how to name amides like you do for esters, but you do need to be able to draw the products of two reactants. So let's take another example of methanoic acid with ethyl amine. I'm going to face the functional groups to each other to make it easy for myself again. And then I'm going to look, there's going to be a water molecule eliminated. So where previously I had a COC bond, now I have a CNC bond and water as my byproduct again. So although you don't need to name amides, we do need to name esters, but we just follow a few simple steps and I think the rules will become clear. In general, we have the name of the alcohol group followed by the parent chain of the carboxylic acid group, and then we add the suffix O8. So, okay, maybe that doesn't make a lot of sense. Let's have a look at how we can break that down with an example into 3 simple steps. And we'll use this ester as an example. So, first step, we're going to identify the oxygen that is part of the chain. That's this COC oxygen. You're going to identify that, circle it. That's going to be where we work outwards from. Next, I'm going to count the carbon chains either side of that central oxygen. So on my right hand side, I can see I have 1, 2, and on my left, I have 1, 2, 3 carbons. So I have a 2 chain on my right and a 3 chain on the left of the oxygen. So the last step is putting the name together with this information. So we're going to find the alcohol group and the carboxylic acid group. So how do we do this? The easiest way is to use the carbonyl group, the C double bond O, to identify the side that is the carboxylic acid, because we know the other side of the molecule that doesn't contain the carbonyl group must be from the alcohol. Then, in this case, we have 2 carbon chains there, so this is going to be an ethyl from the alcohol group is going to come first, and then the other side, which has this carbonyl group, is a 3 carbon chain, so that's going to be propan, and then we're going to add that suffix that I said at the beginning, O8, so we get ethyl propanoate. So let's follow the same rules and try and name another ester then. So with any ester, first thing we're going to do is identify that oxygen that is part of the chain, and that's where we can work out from there to number our carbons on each side. So we have 3 on the left side in this case, and we have 5 on the right side in this case. Now we need to identify which one is the alcohol, which must be the side without the carbonyl group, and that is a 3 carbon chain, so it must be propyl as the first word, and the other side with the carbonyl group must come from our carboxylic acid, which has 5 in this case, so we get pentan, and then we add the O8, so we have propyl pentan O8 as our final name. Let's do a couple of questions on this before we move on to polymerization though. First question, why is sulfuric acid used as a catalyst when making esters? Pause the video. Pop them up. 2 parts to this answer. First is obviously an acid catalyst that speeds up the rate of reaction, but also it's a dehydrating agent, which of course removes water from the reaction and helps to shift the equilibrium to the right hand side, producing more ester. Talking of esters, next question, name this ester. Pause the video to have a go at that. Pop them up! So after we identify the central oxygen, we count our chains either side of that, and we find there is a 2 carbon chain on the left and a 2 carbon chain on the right. So it's actually hard to name this one in particular wrong. We find the one on the right is the alcohol group, and the one on the left is the carboxylic acid group. So we would go from the alcohol is 2 carbons is ethyl, and the carboxylic acid is 2 carbons, so we've got ethanoate. Time to have a go at drawing an ester now, and what I would recommend here is that you draw the 2 molecules, each with their functional groups facing each other first. Pause the video to have a go at that. Pop them up! So like I said, best thing to do, especially when you're first starting, is to draw out the structure of each of these ethanoic acid and propan-1-ol with the OH groups facing each other. And so I'm going to remove a water and then join the carbon from the carbonyl group directly to the oxygen from the alcohol group. And that's going to give me my molecule here, which would be propyl ethanoate if you were naming it. So have a go at naming this ester. Pause the video. Pop them up! So identifying that oxygen in the chain, 3 chain on the left hand side and a 1 chain on the right hand side. Identify the carbonyl group, so that means my chain on the left hand side comes from my alcohol and on the right from my carboxylic acid. Alcohol name goes first, so I'm going to have propyl and then my carboxylic acid group methanoate. Before we move on, have one go at drawing an amide produced from the reaction between ethanoic acid and butylamine. Pause the video to have a go at that. Pop them up. So once again, I recommend drawing the individual molecules out first with their functional groups facing each other, which might make it easier for you to visualize the product. So I've got ethanoic acid on the left, butylamine on the right. Remember, I'm going to remove a water. So in this case, I'm going to have the carbon from the carbonyl group directly bonded to the nitrogen from the amine group, and then each of their chains attached. So if the monomers actually have the correct structure, these reactions can form polymers through a process called condensation polymerization. What we need, however, is we need molecules that contain two functional groups for this to occur. And this makes sense when we think about it. We're going to need on one side of the molecule the reaction to happen, and on the other side of the molecule the reaction to happen to be able to join and continually add more monomers to the chain, forming the polymers. All of these are going to require a dicarboxylic acid. That's a molecule with two carboxylic acid groups, just like how a carboxylic acid was required for both esters and amide production. Then, if we add to that a dialcohol, that's a group with two alcohol groups, we are going to produce polyesters. And if we add to that a diamine, which is a molecule with two amine groups, then we're going to produce polyamides. These are really useful fibers. Indeed, polyamides can be both natural and they can be synthetic. Synthetic examples include nylon, and natural include cotton. So really useful products here. So let's have a look at their formation and how we draw the repeating units of these. We will see some similarities to how we drew the repeating units for the addition polymerization when we looked at alkenes earlier on in the unit. So first, looking at polyesters, we have a dicarboxylic acid and a dialcohol. The R groups here just representing any kind of carboxyl chain or even a benzene ring or anything really. So we draw a square bracket just as we did before, drawing a bond in, and then we're going to do the same thing we did before when we drew the products, except on either end of the molecules. So both the OH group in the carboxylic acid group on the dicarboxylic acid and the OH group on the diol, we're going to remove the water from the ends as well. And then we can just draw carbon by carbon the chain in the middle, remembering to remove the water just as we did before in the center of the molecule, and put a square bracket and an N around the end to indicate that this is one repeating unit of our polyester. A good way to double check if you've got this right at the end is to imagine translating your square bracket to either the left or to the right, and does the bond that goes from one bracket to the other in that case match the bond in the middle of the molecule, and if it does, then it looks like you've drawn the correct repeating unit. Drawing a polyamide follows exactly the same process except with a diamine. So we still have a dicarboxylic acid with an R group in the middle, and we have a diamine with an R group in the center too. And again, we're going to eliminate water and bond the carbon directly to the nitrogen, but we're also going to remember to eliminate the water from either end of the molecule as we did before, and then draw our square brackets and then translate each of the carbons down into a long repeating chain. Now remember, if we want to check if our individual repeating unit is correct, then we can visualize sliding it to the left or right, and does it bond with the same bond? If you do that, that does in the middle. In this case it does, so we have our polyamide repeating unit. An example of a polyamide we can have here with our dicarboxylic acid with the benzene ring in the middle, and our diamine also with a benzene ring in the middle. We have benzene 1,4 dicarboxylic acid and 1,4 diaminobenzene. When these are polymerized, we just remove the water from the center, draw our square brackets. Effectively, R or R dash has just become a benzene ring in this case. This repeating unit is the repeating unit for Kevlar, which when it's put into a laminate configuration can be very resistant to projectile impacts and can form a lightweight bulletproof protection that's much lighter than that of an equivalent steel plate. Some of the biologists among you may have already noticed that amino acids indeed have both an amine and a carboxylic acid group. Indeed, they're the OG of the condensation polymerization game. If we change the R group, then we end up with a different amino acid. We have an amine and a carboxylic acid group, so we don't even need a dicarboxylic acid or a diamine. Indeed, amino acids can polymerize with themselves or with other amino acids that have a different R group to form polypeptide chains and go on to obviously fold and form further protein structures. So this is one of the fundamental building blocks of life and organisms. So let's do a couple of questions on polymerization. First question, what kind of polymer would you expect from the reaction of butane 1,4-dioic acid and hexane 1,4-diol? Pause the video to have a little think. Pop them up. So hopefully you saw here we've got a dioic acid and a diol. So carboxylic acid plus an alcohol makes an ester. So we would expect a polyester. So from that same reaction, have a go at drawing the single unit repeat polymer. Pause the video to have a go at that. Pop them up. So just like before, I'm going to draw out the individual monomers first and make sure we get the structures of those correct. Watch out, in this question, it does say hexane 1,4-diol. So I'm going to have the OH groups on the first and the fourth carbon. Then I draw my square brackets as I did before. Remember to take the water off of each end and also in the center for your ester bond, and your square brackets with your N at the final part to indicate that it's the repeating unit. One more question. Draw the repeat unit with the same dicarboxylic acid but with pentane 1,5-diamine. Pause the video to have a go. Pop them up! Once again, I'm going to draw both of the monomers out first with the R groups condensed here for the sake of ease. And then we're just going to remember we're going to remove the water, which is going to have the CN-C bond, square brackets, remembering to remove the water from each end of the molecule, drawing in the whole molecule, and then N with a square bracket at the end to indicate the repeating unit. So esters often have a very pleasant smell, so there is some practical work that we would be doing on fruity esters, so make sure you have a look at that. Thanks for joining me again, guys. Please like, subscribe, share the video, and as always, practice makes slightly better.